Thank you for watching my popular science presentation. This presentation is my attempt at distilling and communicating my PhD research on local learning algorithms for emerging hardware in a hopefully accessible fashion. Motivation for my research project comes from biology and neuroscience, where it's known that biological neural networks are very different from artificial neural networks. The brain both involves rapid feed-forward processing driven by sensory input, but it also involves feedback and general recurrent connectivity believed to be responsible for higher level cognition, memory, and attention. Today, recurrence is somewhat underexplored, and when it is employed in artificial neural networks, it is trained in a way that requires backtracking through the temporal dynamics. This is memory costly on digital hardware, and on analog hardware it is outright impossible. My research has focused on developing ways to train recurrently connected networks without needing to unfold the temporal dynamics. A bit of context, I will give a super brief history of computing. So early computers were analog, meaning states could take a smooth range of values. Think, for instance, of a voltage that can take any value between 0 and 5 volts. Having continuous states, analog computers are non-deterministic. This means you can run the same program twice and you may get different outcomes each time. Usually just slightly different, but different nonetheless. These devices are hardwired to solve specific problems, for instance, to compute ballistics trajectories. And to solve a new problem, you would have to physically rewire the machine. Digital computers came into fashion in the 40s and have been omnipresent since. They have discrete states, typically either 0 or 1, though ternary variants with the states -1, 0, and 1 have also been explored. These discrete states is part of the reason why they can implement deterministic programs. So you run the program twice and you get the same result each time. With the advent of stored programs, it also became possible to run many different programs on the same machine without physically altering the machine, which has been instrumental in getting computing widespread. In more recent times, we have seen the development of a variety of specialized digital computing architectures in which many processors divide the work between each other. For instance, graphical processing units and tensor processing units have been very instrumental in accelerating AI workloads. So what comes next? I believe that the future will see a lot more diversity in the compute landscape. I think part of this compute landscape will be occupied by analog hardware, which can allow fast and energy efficient and inherently recurrent artificial intelligence to be developed. But as mentioned, this will require new training algorithms, which is what I have been working on. AI researcher Andrej Karpathy introduced the concept of neural networks as software 2.0, as opposed to traditional software 1.0, in order to highlight the distinction between the fundamentally different ways these kinds of software gets created. So software 1 is written by humans, and if you know how to program, you can read the source code. Software 2.0, on the other hand, is written by an algorithm called gradient descent, and the programs are just numbers stored in massive arrays, and this is not in general human readable. Two distinctions: analog and digital, and software 1.0 and software 2.0. I find it useful to look at these two dimensions jointly when thinking about the compute landscape of the past, present, and the future. This jointly, then we have in the analog software 1.0 bucket raw hardwired circuits. In the software 1.0 digital computing bucket, We have traditional softwares like Word and your internet browser, etc. In the digital software 2.0 bucket, we have your neural networks, ChatGPT, for instance. And then there's this other bucket, software 2.0, analog computing, where analog neural networks fit in. And the key observation here is that a lot of what digital computing brings you, that is discrete states and determinism, those are not actually things you need in order to implement neural networks. Sometimes they can be nice to have, but you don't need them, and they tend to increase the energy consumption of your hardware. So when we can, it's beneficial to move to analog, though that puts some constraints on how you can train your hardware. For a digital neural network, you would have some input data that could be an image of a dog, for instance, and some input neurons which would encode this image, for instance, by simply flattening it into a long vector. Then at the first time step of your feed-forward network dynamics, the signals would travel via a matrix vector multiplication to the next layer. And at the next step, the signals would go one layer deeper. And at step 3, it would reach the output, at which time you would look at what the network is saying. In this case, the network is saying that it thinks it's a cat, which means it's quite wrong. So based on this prediction, we would compute some error signal that tells the network how to update the weights, and we will propagate that backwards through the layers, one layer per time step here. This works very well on digital hardware, but it doesn't map well to analog hardware. On analog hardware, we have to do things quite differently. Analog circuits, on the other hand, we don't have a global clock. Rather, the neural states evolve continuously, and error and activity signals flow in both directions simultaneously. Network predictions are found by letting the network relax to an equilibrium state, exploiting the physical processes of whatever hardware you have chosen to work with. It's typically done by measuring the neural states twice while subject to different boundary conditions. So first we might fix the input units to some input data and measure the states following relaxation. Subsequently, we might inject some teaching signal and then again let the circuit relax to an equilibrium state. And then afterwards we would adjust the weights, that is the synapses connecting the neurons, in order to make the correct predictions more likely and to make the incorrect predictions less likely. My research has focused on deriving such contrastive learning algorithms by formulating neural network training as constraint optimization problems. Depending on the constraints you impose on the neural dynamics, you get algorithms with very different properties. You can, for instance, get neuron and weight updates that are both local in space and time, which is often desirable for analog hardware. In my field, feedback is often either neglected or restricted to be symmetric with the forward connectivity. Both of these options are highly biologically implausible. So I'm very interested in exploring alternative types of asymmetric feedback. This is not only motivated by biology, but also from the engineering field of control theory, where it's well known that asymmetric connectivity can endow circuits with interesting properties, most notably make them more stable and robust to perturbations. Thank you very much for listening to this high-level overview of my PhD research topic. I hope it made sense. I hope it made you curious about analog computing and about learning algorithms in general.